1 hour of absurd facts that sound true, but aren't some beliefs, survive because an object seems to explain itself. A laser dot looks like it measures temperature. A tiny packet looks like it soaks up moisture like a sponge. A mirror seems to know who is allowed to see through it, and a smoke alarm seems like it can smell smoke. This time, we're going through 45 completely different facts built around everyday objects, materials, sensors, and machines. The goal isn't just to say, that's wrong. Each one has its own reason for sounding believable, its own weak point, and a real mechanism that changes what you thought you were looking at. Fact number 1. The red laser dot on an infrared thermometer is the beam that touches the object, measures its temperature, and sends the reading back to the screen. Point 1 at a cast iron skillet, and the story seems obvious. A red dot lands exactly where you're aiming, then a temperature appears a second later. Visually, it looks like the laser did the measuring. That also fits what we already know about other optical devices. Send out a signal, let it hit something, then read what comes back. But there's a problem. Many infrared thermometers still work when the aiming laser is turned off. And the visible dot can be much smaller than the actual area the sensor is averaging, especially as you move farther away. The thermometer is really detecting infrared radiation emitted by the surface within its field of view. Its electronics then estimate temperature using calibration assumptions that can depend on factors such as emissivity. Shiny or reflective surfaces can fool the reading because the radiation reaching the sensor may not represent the object's temperature in a simple way. The red dot is basically a pointer. The real thermometer is looking at a part of the spectrum your eyes cannot see. Fact number 2. A home water softener removes almost every contaminant and turns tap water into purified water all by itself. If you've ever lived in a part of the U.S. with hard water, the difference after installing a softener can feel dramatic. Scale builds up more slowly on faucets and water heaters. Soap behaves better. Fixtures look cleaner. That visible improvement makes it easy to assume the system has cleaned everything out of the water. But ask one simple question. What happens to a contaminant that is not calcium or magnesium? A standard household water softener mainly works through ion exchange. The resin trades ions responsible for hardness, especially calcium and magnesium for other ions. That solves a specific problem. It does not automatically disinfect the water, remove every particle, perform reverse osmosis, or eliminate every organic compound or metal. Water treatment only makes sense when you know what problem you are treating. A softener answers, how hard is this water? Purification requires a much longer list of questions. Fact number 3. A carbon monoxide alarm will always warn you if natural gas or methane is leaking inside your home. The confusion is understandable. Both hazards are tied to fuel. Both can be deadly. And both alarms may look like small plastic boxes mounted on a wall or plugged into an outlet. On top of that, faulty combustion involving natural gas can produce carbon monoxide, so the two risks become linked in people's minds. But a home can have methane escaping without carbon monoxide being produced at that moment. So what exactly would a sensor designed for a different molecule be detecting? Standard carbon monoxide alarms are designed to respond to carbon monoxide. They are not universal combustible gas detectors. Methane, propane, and other fuel gases require sensors designed for those gases. Combination devices do exist, but you have to check what the label says they actually detect. A silent CO alarm does not prove there is no fuel gas leak. Two gases can be dangerous in the same kitchen and still require different sensors. The label matters more than the shape of the box. Fact number 4. Those little silica gel packets work like microscopic sponges that soak liquid water into a soft material. Open a new pair of shoes, a box of electronics, or a bottle of vitamins, and you may find a packet that says, "Do not eat." Everyone knows its job is to fight moisture. And because a kitchen sponge is our everyday model for soaking up water, the comparison feels natural. But the beads inside stay hard. They do not swell into soggy little cushions, and they do not hold a visible puddle inside themselves. Silica gel is a porous solid with an enormous internal surface area. Water molecules are held mainly on those surfaces through adsorption. That is different from absorption. where a substance is taken into the bulk of a material. Under the right conditions, some of that absorbed water can be driven off with heat, which is why certain desiccants can be regenerated. The packet is not a tiny sponge. It is more like a molecular parking garage with an absurd number of spaces hidden inside. Fact number 5. Every RFID tag needs a tiny battery in order to transmit its identification by radio. Tap a badge near a reader, or pass a tagged item through a scanner, and information appears without any physical connection. Since radio transmission requires energy, it seems obvious that the tag must be hiding a battery somewhere inside. That analogy works for your phone, Bluetooth earbuds, and plenty of other wireless devices. So why not RFID? Because many RFID tags are passive. They do not carry their own battery. The tag's antenna captures energy from the radio frequency field generated by the reader. The chip uses that energy to operate, then changes or backscatters the signal in a way the reader can interpret as data. Active and semi-passive RFID tags with batteries also exist, but they are different categories with different ranges, costs, and use cases. That is why millions of thin, inexpensive tags can work for years without anyone replacing a battery. A passive RFID tag does not bring its own fuel. It waits for the reader to show up with the energy. And now the next trap gets even better. Transparent objects and everyday materials whose names seem to tell you exactly what they are, even when their structure says otherwise. Fact number 6. A one-way mirror has one side that always reflects and another side that always lets you see through, no matter how the rooms are lit. Crime shows have trained generations of viewers to accept the effect instantly. A suspect sees a mirror. Detectives on the other side watch through it. The phrase one-way mirror makes it sound like the glass has a permanent direction built into it. But change the lighting and the illusion can fall apart. Brighten the observer's side and darken the room on the other side, and privacy can disappear. These setups generally use glass that is partly reflective and partly transmissive. The practical effect depends heavily on a strong difference in brightness. On the brightly lit side, your own reflection dominates what you see. From the darker side, light coming from the bright room can be much easier to see through the glass. The coating does not know who is a detective and who is a suspect. The brightness difference is doing most of the work. It is not glass with loyalties. It is optics taking advantage of the fact that your eyes notice the brighter image first. Fact number 7. Ordinary window glass is a crystal with atoms arranged in a repeating lattice, basically like quartz but transparent. Glass is hard, rigid, and can break into sharp, shiny pieces. We even use the word crystal casually for certain kinds of glassware, so it is easy to assume that anything clear and solid must also have a crystal-like internal structure. But when you examine ordinary glass at the microscopic level, you do not find the long-range repeating order that defines a crystalline solid. Common glass is an amorphous solid. As it cools from a liquid, its structure becomes locked into a disordered arrangement instead of forming a repeating crystal lattice. That does not mean glass is secretly a liquid flowing at an unbelievably slow rate. It means its atoms lack the long-range periodic pattern found in true crystals. Quartz and silica glass can be dominated by similar chemistry while still having very different internal structures. Your window is rigid like a solid and disordered like a frozen snapshot of a liquid. Transparency does not automatically mean crystallinity. Fact number 8. Plaster of Paris hardens only because the water evaporates, the same way a wet patch dries. Mix the white powder with water and you get a smooth paste. Leave it alone and, not long afterward, it becomes rigid. From the outside, that looks exactly like drying. Plenty of paints, clays, and coatings become firmer as water or solvent leaves, so using the same explanation for plaster seems efficient. But plaster can warm up while it sets, and it can gain strength before all the added water has had time to evaporate. That tells you something else is happening. Plaster of Paris is mainly calcium sulfate hemihydrate. When mixed with water, it rehydrates and forms crystals of gypsum, calcium sulfate dihydrate. Those crystals grow and interlock, creating the solid structure. Later loss of free water helps with final drying, but the initial setting is tied to hydration and crystallization. Saying it dried describes what it looks like. It does not describe the full mechanism. The plaster is not just waiting for water to leave. It is using some of that water to rebuild a crystal network. Fact number 9. Plexiglass is real glass, made with a different process, so it can be lighter, tougher, and more flexible. It is clear. It is used for windows, display cases, barriers, and protective panels. Even the name ends in glass. When two materials do the same optical job, the brain naturally groups them together. But heat it, machine it, or expose it to certain solvents, and it behaves very differently from ordinary silicate glass. Plexiglass is a trade name associated with PMMA, or polymethyl methacrylate. That is a transparent thermoplastic polymer. Its density, impact behavior, thermal response, and manufacturing methods belong to the world of plastics, not traditional silicate glass. It can replace glass in many applications precisely because a different chemistry can still produce excellent transparency. That is also why it can be cut, polished, and thermoformed using techniques designed for engineering plastics. Plexiglass shares a job with window glass. It does not share the same family tree. Fact number 10. Sandpaper is literally made by gluing ordinary sand onto paper. The name sounds like a complete recipe. Sand plus paper. The surface looks grainy, it scratches like sand, and early coated abrasives really did use natural abrasive materials. That historical truth makes the modern assumption even easier to accept. But think about how differently one sheet of sandpaper can behave from another when working on wood, automotive paint, metal, or glass. Beach sand would be far too inconsistent in hardness, shape, and wear to give manufacturers that level of control. Modern coated abrasives often use engineered or carefully selected materials such as aluminum oxide and silicon carbide. Certain products also use natural abrasives such as garnet. The particles are graded by size and bonded to a backing with adhesive systems designed for the job, and paper is not universal either. Backings can include cloth, fiber, film, and other materials. Sandpaper kept a historical name while materials engineering quietly replaced most of what the name seems to promise. The next 5 move from the workshop to your closet, spice rack, and backyard. Fibers, plants, and foods with names so convincing that we rarely stop to check their chemistry or family tree. Fact number 11. Rayon is a petroleum-based synthetic fiber basically like polyester, just softer. Look at a clothing label, and rayon appears alongside nylon, polyester, acrylic, and other manufactured fibers. Since none of them comes off a sheep or straight out of a cotton boll ready to spin, it is convenient to throw them into one big synthetic category. Rayon also requires serious industrial processing, which makes it sound like plastic from the start, but the raw material changes the story. Rayon is made from cellulose, often derived from plant pulp. That cellulose is chemically processed, dissolved or transformed, and then regenerated into filaments. That is why rayon is commonly classified as a manufactured regenerated cellulose fiber. Polyester is different. It is a synthetic polymer from another chemical family. So natural and synthetic do not form a simple straight line once a biological raw material goes through an industrial process. Rayon is not untouched cotton, and it is not polyester wearing a softer costume. It is cellulose that has been chemically taken apart and spun back into fiber. Fact number 12. Anything made of fiberglass is basically solid glass molded into a tougher shape, so if it breaks, it should behave like a thick window. The name seems literal, fiber plus glass, and the individual reinforcing fibers really are made of glass. That true part makes it easy to overlook what the rest of the object is made from. Think about a fiberglass boat hull, ladder, body panel, or shower enclosure. It can be opaque, relatively light, and when damaged it may expose strands and torn-looking material. That does not resemble a shattered sheet of window glass. Many products called fiberglass are composites. Fine glass fibers provide reinforcement inside a polymer resin matrix. The fibers add strength and stiffness in useful directions. The resin holds the shape, transfers loads, and protects the reinforcement. Fiberglass insulation can use glass fibers in a different architecture without the same kind of structural resin matrix, so the name covers more than one material system. The glass often provides the microscopic skeleton. In many rigid parts, a polymer builds the body around it. Fact number 13. Pink peppercorns are simply berries from the same plant that produces black pepper, picked at a different stage of ripeness. Walk through the spice aisle and you may see black, white, green, and pink peppercorns mixed together in one grinder. The colors look like 4 versions of the same ingredient. And black, white, and green peppercorns really are closely connected to Piper nigrum and differ largely because of ripeness and processing. That makes pink seem like the obvious 4th member. But many commercial pink peppercorns come from trees in the genus Scynus. Species such as Scynus mole and Scynus terebinthifolia produce small aromatic fruits sold as pink peppercorns because of their appearance and culinary use. They are not fruits of Piper nigrum. The culinary name describes resemblance and function, not botanical identity. Depending on the product and region, pink peppercorn can refer to somewhat different plant sources, so the label is worth checking. The spice grinder got a beautiful color palette. Botany got a much messier family reunion. Fact number 14. Mistletoe is completely independent and only uses a tree branch as physical support. You can see mistletoe staying green even after its host tree has lost its leaves. Since it has its own leaves and can photosynthesize, it looks like a self-sufficient tenant that simply chose a convenient place to live. That would make it similar to true epiphytes, such as many orchids, which mainly use other plants for support without tapping directly into their vascular system. But look at where mistletoe connects to the branch, and the relationship becomes much less innocent. Many mistletoes are hemiparasites. They perform photosynthesis and make much of their own organic material, but they also develop structures called haustoria that penetrate the host and draw water and minerals, especially from the xylem. Heavy infestations can impose real costs on a tree, particularly during drought or other stress. Mistletoe is not completely dependent, but it is not completely independent either. It pays for part of its own food with photosynthesis. The plumbing, however, belongs to the neighbor. Fact number 15. Mangroves thrive because their roots absorb seawater along with all its salt, and the plant simply uses that salt like an ordinary nutrient. Mangroves grow with their roots in salty or brackish water, sometimes for decades. From the outside, that looks like proof that salt no longer bothers them. If a plant can live there, surely it must have learned to drink seawater the way a houseplant drinks tap water. But salt still creates serious osmotic and ionic problems, even for plants adapted to salty environments. The real question is not, do mangroves like salt? It is, how do they keep salt from winning? Different mangrove species use different strategies. Some exclude much of the salt at the roots. Others allow more salt to enter and then excrete part of it through leaf glands, or isolate it in tissues that can later be shed. They also adjust their physiology to take up water under difficult osmotic conditions. There is no single universal mangrove filter, but the shared theme is active salt management. Mangroves did not turn the ocean into fresh water. They turned salt control into a survival specialty. After the plants come animals and everyday names that try to do taxonomy by appearance. This is where a, quote, house, a one-day life, and even the word ant start falling apart. Fact number 16. A snail carries its shell like a separate house that it could leave behind and replace with a larger one. The mental picture is basically a hermit crab. There is a soft animal inside a hard structure, so it feels natural to imagine the shell as portable real estate. A snail can extend much of its body out through the opening, which makes the shell look even more like a container it happens to be living in. But trying to separate a living snail from its shell is not the equivalent of making it temporarily homeless. The shell is anatomically connected to the animal. The mantle secretes the calcium-rich material that builds and maintains it, and the shell grows as the snail grows, adding material mainly around the opening while other regions thicken. Muscles and internal tissues are attached to it. Minor shell damage can sometimes be repaired, but losing the entire shell is not like moving out of an apartment. Hermit crabs occupy shells made by other animals. Snails build their own. A snail is not carrying luggage, it is carrying a mineralized part of its own body. Fact number 17. Mayflies are born, live, and die within a single day. The one-day insect is one of those facts that sounds so perfect it gets repeated without much inspection. In many species, the winged adult stage really is remarkably short. Large swarms can appear, reproduce, and seem to vanish almost overnight. If that is the only stage you ever see, it looks like an entire lifetime compressed into a few hours. But the clock did not start when the insect began flying. Mayflies spend most of their lives underwater as aquatic nymphs. During that stage, they feed, grow, and molt repeatedly. Depending on the species and environmental conditions, the nymphal period can last for months and sometimes considerably longer. The final winged adult stage may last only hours or a few days and is focused largely on reproduction. So saying a mayfly lives for one day can describe the visible adult chapter fairly well in some species, while badly misrepresenting the whole life cycle. The mayfly does not necessarily have a one-day life. It has such a short, dramatic finale that we forgot about everything that happened underwater first. Fact number 18. Silverfish are called silverfish because they eat silver, metal, or minerals stored around the house. The accusation practically writes itself. They show up in drawers, basements, bathrooms, closets, and old boxes. Their bodies have a silvery sheen, and plenty of pest names tell you exactly what the animal attacks. Clothes, moths, flower beetles, rice weevils. So silverfish sounds like it should mean a creature with an expensive appetite. Except the damage tells a different story. Silverfish are insects in the order Zygentoma. They feed on materials containing carbohydrates and proteins, including paper, book bindings, adhesives, starches, food residue, treated fabrics, and organic debris. That is why they can become a nuisance around books, cardboard, stored paper, and humid storage spaces. The silver part mainly describes their scales and appearance. The fish part refers to their quick, wiggling movement. Neither word makes them fish, and neither word means they are chewing through your flatware. The name sounds like a menu. It is really just a surprisingly imaginative description of how the insect looks and moves. Fact number 19. An antlion is a giant predatory ant that digs sand traps to catch other ants. The name does a lot of misleading work. The larva lives in sandy soil, often catches ants, and in some species builds the famous cone-shaped pit traps. If you rarely see the animal itself, ant that hunts ants sounds like a decent guess. Then the insect completes metamorphosis. What emerges is not a larger ant from a hidden colony. Adult antlions are slender, winged insects in the order Neuroptera, related to lacewings rather than ants in the order Hymenoptera. In the species famous for pit building, the larva waits beneath loose sand with large jaws ready to grab small arthropods that slide into the trap. Later it pupates and transforms into a delicate-looking winged adult that can remind people of a damselfly. And not every antlion species builds pits. That strategy is famous, not universal. The adult and larva can look so different that, without knowing the life cycle, you might assume they are unrelated animals. Antlion describes what impressed us about the hunter. It does not describe its family tree. Fact number 20. Polarized sunglasses are just ordinary sunglasses with a darker tint, which is why they cut glare better. Put on a good pair while driving past wet pavement, looking across a lake, or standing near the ocean, and the glare can drop dramatically. The simplest explanation is that the lenses are just blocking more light. Darker equals less brightness, and less brightness should mean less glare. That seems complete. But two lenses with similar overall darkness can behave very differently when you look at a strong reflection from water or a road surface. Polarization is selecting more than just the amount of light. A polarizing filter preferentially transmits certain orientations of the electric field in light. Reflections from non-metallic surfaces such as water and pavement can become partially polarized. When the filter is oriented appropriately, it can block a large portion of that reflected glare. Lens darkness, UV protection, and polarization may all be features of the same pair of sunglasses, but they are not the same property. A dark lens turns the volume down. A polarized lens also tries to mute one particular direction of optical noise. Now the confusion moves directly into light itself. Polarization, photochromic lenses, and fluorescence look a little like magic until you follow what the photons are actually doing. Fact number 21. Transition-style lenses get darker outdoors, mainly because they heat up in the sun. You walk out of an office or store on a bright day, and your glasses begin to darken. Sunlight and heat usually arrive together, so they warm up and change color feels like the obvious explanation. And temperature really can affect how these lenses behave, which makes the fact even more convincing. But there is a useful clue inside a car. You can have plenty of visible light and heat behind a windshield, while some photochromic lenses darken much less than they do outdoors. The reason is that many photochromic technologies are activated mainly by particular wavelengths of light, especially ultraviolet radiation. Molecules in the lens change structure or state when they absorb that radiation. When the activating light decreases, they gradually return toward their original state, and the lens clears. Temperature can influence how fast and how strongly the transition happens, but it is not the same thing as the main optical trigger. That is why performance can differ in winter, summer, and behind different types of glass. Heat changes the performance. Light usually hands the lenses the script. Fact number 22. A black light does not emit real light. It just makes hidden substances glow using some mysterious dark energy. Turn one on, and the room may still look almost dark, while white shirts, teeth, inks, and fluorescent materials suddenly light up. Because the lamp itself does not seem very bright, the glow appears to come from the objects rather than from illumination hitting them. Our eyes are terrible judges of energy outside the wavelengths we can see. Black lights emit mostly long-wave ultraviolet radiation, commonly UVA, along with some visible violet light depending on the design. Your eyes are either very insensitive to much of that ultraviolet or cannot see it at all. Fluorescent materials absorb those higher energy photons and then re-emit part of the energy at longer, visible wavelengths. That is why the objects appear to switch on. They are not producing brightness from nothing. They are converting incoming radiation that your eyes could not see into light that your eyes can see. The room is not without light. It is full of light for which human vision is a pretty lousy audience. Fact number 23. Fluorescent highlighter ink glows because it stores light and slowly releases it later. Run a yellow highlighter across white paper, and the mark can look almost brighter than the page around it. Under a black light, the effect becomes even stronger. That makes it easy to picture the ink charging up like a tiny optical battery. And glow-in-the-dark materials really do exist, so fluorescence and phosphorescence often get tossed into the same mental category. But turn off the exciting light source, and an ordinary highlighter stops glowing essentially right away. It does not keep shining for minutes like a glow-in-the-dark sticker. Fluorescent dyes absorb higher energy photons and rapidly re-emit part of that energy at longer wavelengths in the visible range. The emission continues while the material is being excited and dies away extremely quickly after the excitation stops. Phosphorescence involves different electronic states and longer-lived processes that allow an afterglow to persist. A highlighter is not saving light for later. It is transforming light almost in real time, which is why the color can seem to shout louder than the paper around it. Fact number 24. A disposable diaper works mainly because it is stuffed with a huge amount of cotton or compressed paper. Pick one up, and it feels like a soft white pad full of fibers. For generations, cloth and cotton were exactly what people used to absorb liquid. So it feels natural to imagine a modern diaper as the same basic idea with more layers and better packaging. But the numbers do not make sense if fibers are doing all the work. A modern disposable diaper can hold a large amount of liquid without needing to be as bulky as a bath towel. Many absorbent cores combine fibrous material with superabsorbent polymers. Materials such as sodium polyacrylate can take in large amounts of water into a swollen polymer network, turning free liquid into a relatively immobile gel. The diaper also uses other layers to move liquid away from the surface, distribute it through the core, reduce contact with skin, and help contain it. Exact designs vary by brand and generation. The fibers help move and distribute the liquid. The polymer performs the trick that plain cotton would need far more volume to imitate. Fact number 25. Sparkling water gets its bubbles because ordinary air is pumped into the bottle under pressure. Open a bottle and transparent bubbles rush upward. They look exactly like the bubbles you would make by blowing air through a straw. Since normal air already contains some carbon dioxide, saying compressed air sounds close enough for a kitchen explanation. But the flavor gives away the real story. Classic carbonation is created by dissolving carbon dioxide in water under pressure. When you open the container, the pressure above the liquid drops, and dissolved carbon dioxide begins escaping, forming bubbles at nucleation sites. Some of the dissolved carbon dioxide also participates in equilibria that form carbonic acid, contributing to the characteristic bite and acidity. Other beverages may use nitrogen for a different texture or effect, sometimes alongside carbon dioxide, but ordinary carbonated water is primarily about carbon dioxide, not generic air. The bubbles look like air because gases are invisible. The taste tells you the bottle chose a very specific molecule. The next 5 turn a cold mist, a ball bearing, and 2 force-multiplying machines into one simple lesson. Reducing a loss does not mean eliminating it, and multiplying force does not create energy. Which of these explanations would you have repeated with complete confidence before looking inside the mechanism? Save your answer for the comments, because there are still 20 twists left, and several of them sound obvious right up until we open the box. Fact number 26. Obsidian is a black mineral crystal, basically a dark volcanic version of quartz made from large crystals. It is shiny, it can look glassy, and it fractures into extremely sharp edges. Rock shops often display it next to minerals and objects casually labeled crystals. Since it comes from lava, and many volcanic rocks contain crystals, the assumption feels reasonable. But its internal structure tells a different story. Obsidian is volcanic glass. It forms when silica-rich lava cools quickly enough that its atoms do not have time to organize into an extensive crystal lattice. The result is largely amorphous, rather than a single giant crystal. That lack of a regular crystalline cleavage structure helps explain its conchoidal fracture and famously sharp edges. Obsidian can contain inclusions or small crystals, depending on how it formed, but those do not turn the entire mass into one crystal. The volcano supplied the chemistry. Rapid cooling denied the atoms enough time to organize. Obsidian came out of a volcano and became glass before its atoms could hold a proper meeting. Fact number 27. The white cloud from an ultrasonic humidifier is hot water vapor, just like the steam rising from a pot on the stove. The machine turns water into a visible cloud that floats into the room and disappears. In everyday speech, we call almost any visible wet cloud steam, so boiling water seems like the obvious mechanism. But the reservoir and mist can stay cool. There is another clue. If you fill some ultrasonic humidifiers with mineral-rich water, you may eventually notice white dust settling on furniture. An ultrasonic humidifier uses high-frequency vibrations to create extremely small liquid water droplets. Those droplets form a cool aerosol. They may evaporate after entering the room, but the visible cloud itself is not pure molecular water vapor. Because the droplets begin as liquid water, dissolved minerals can travel with them and be left behind after the water evaporates. Warm mist humidifiers use a different mechanism. An ultrasonic humidifier is not secretly boiling water without heat. It is breaking liquid into droplets so tiny that, for a moment, they look like a cloud. Fact number 28. Ball bearings eliminate friction because they replace sliding with rolling. Spin a skateboard wheel, bicycle hub, or good machine bearing, and it can keep moving with remarkably little effort. Compared with two flat surfaces scraping past each other, rolling looks like a complete victory over friction. And rolling resistance can indeed be much lower than sliding friction. The mistake is turning much lower into zero. The wheel eventually stops even with a new, well-lubricated bearing. Energy is still being dissipated. Bearings reduce losses by controlling how rings and rolling elements contact one another. But several sources of resistance remain: elastic deformation, tiny amounts of microslip, lubricant shear, seal friction, and losses that depend on load, speed, alignment, and preload. A well-designed bearing does not beat thermodynamics. It simply manages losses far more efficiently. Engineering rarely needs friction equals zero. It needs friction low enough, predictable enough, and controllable enough for the job. The ball bearing did not abolish friction. It turned a messy fight into a very efficient negotiation. Fact number 29. A hydraulic jack creates extra force out of nowhere because a small push can lift a car weighing thousands of pounds. You pump the handle with ordinary human effort, and several thousand pounds of metal rise off the ground. If you focus only on force, it can look like the machine is giving you far more than you put in. The force multiplication is real. The free energy is not. In a hydraulic system, pressure applied to a confined fluid can act on a larger piston area and produce a larger output force. But the larger piston moves a much shorter distance. That is the trade. In an ideal system, the work going in and the work coming out balance. In a real jack, friction, fluid losses, deformation, and other inefficiencies mean you actually get a little less useful energy out than you put in. The jack trades distance for force. You move the small piston through a greater total distance, so the large piston can move a heavy load through a smaller distance. It lifts the car because you agreed to pump farther, so the other side could move harder. Fact number 30. A reduction gearbox increases torque, so it must also create more mechanical power at the output. A small motor that cannot start a heavy load directly may do it easily after you add gears. The output shaft can push much harder, so it feels as though the gearbox has amplified everything. In everyday conversation, torque, force, and power often blur together. But look at what happened at the same time. The output shaft got slower. A gear reduction trades angular speed for torque. In an ideal system, mechanical power, torque multiplied by angular speed, is conserved. In a real gearbox, the output power is slightly lower because of friction and other losses. The gearbox can match a motor to a load and make a task possible without creating energy. A higher gear ratio is not a watt amplifier. It gives you a stronger arm and slower legs. The energy bill still arrives. From here, we move into filters, sensors, and alarms, small boxes that look as if they understand the world. The interesting part is figuring out what physical quantity they are actually measuring. Fact number 31. A catalytic converter cleans exhaust by filtering pollutants into a sponge or mesh that stores the dirty material inside. It sits in the exhaust system, and its job is to clean up emissions. That sounds exactly like a filter. Dirty stuff goes in, cleaner stuff comes out, and the contamination stays trapped somewhere inside. Air filters and particulate filters really do work by physically capturing material, so it is easy to blend all of these devices into one mental picture. But gases such as carbon monoxide and nitrogen oxides could not simply accumulate forever inside a small metal can without the device quickly filling up. A catalytic converter works differently. Catalytic surfaces accelerate chemical reactions that transform pollutants into other substances. In a typical three-way catalytic converter operating under appropriate conditions, carbon monoxide and certain hydrocarbons are converted mainly into carbon dioxide and water, while nitrogen oxides are reduced toward nitrogen. Particulate filters are separate technologies, although modern exhaust systems may combine several emissions control functions. The catalytic converter does not store the chemical trash. It persuades molecules to leave with a different identity. Fact number 32. Activated carbon absorbs every contaminant, kills microbes, and automatically makes water or air completely pure. Activated carbon shows up everywhere. Pitcher filters, aquarium filters, range hoods, respirators, and air purifiers. When one material appears in that many products, it starts to look like a universal chemical eraser. Its black color and enormous porosity make the image even stronger. If an odor disappears after passing through carbon, why would any unwanted molecule survive? Because different substances interact with carbon very differently, and the material has a finite capacity. Activated carbon works mainly through adsorption. Its porous structure provides a huge internal surface where certain molecules can stick. How well that works depends on the chemistry of the contaminant, its concentration, contact time, humidity, temperature, and the design of the carbon itself. It can be extremely useful for certain organic compounds and gases, but it is not a universal barrier for dissolved salts, every metal, all particles, or pathogens. That is why treatment systems often combine technologies. Activated carbon is not an infinite chemical vacuum cleaner. It is a gigantic surface with preferences, limited space, and eventually a need for replacement. Fact number 33. Melamine dinnerware is a type of lightweight ceramic because it is hard, smooth, and rigid. A melamine plate can look a lot like ceramic from across the table. It holds its shape for years, feels solid in your hand, and does not match the stereotype of plastic as something soft and flexible. So the brain makes a quick classification. Rigid means ceramic, flexible means plastic, materials science is less cooperative. Melamine tableware is commonly made from thermosetting melamine formaldehyde resin. During molding and curing, the polymer forms a rigid cross-linked network. Once cured, it does not behave like an ordinary thermoplastic that can simply be melted down and reshaped. Its hardness and finish can imitate part of the experience of ceramic dinnerware, but chemically it remains a polymer-based material rather than fired clay or another ceramic body. Specific food use recommendations depend on the product and applicable safety guidance, but the basic classification is clear. Rigidity does not grant ceramic citizenship. Some plastics simply learned how to sound very serious when you set them on the dinner table. Fact number 34. A PIR motion sensor detects people by sending out an invisible infrared beam and waiting for someone to break it. That little white dome in the corner turns on a porch light or security system when you walk by. The behavior feels exactly like the laser tripwires you see in movies. And some motion sensors really do transmit ultrasound, microwave energy, or light. So if this one says infrared, it seems logical that it must be shining invisible infrared into the room. But the P in PIR stands for passive. A passive infrared sensor mainly watches changes in infrared radiation arriving from its surroundings. A segmented lens directs different parts of the field of view onto the sensing element. When a warmer body moves from one zone to another, the infrared pattern changes, and the electronics can interpret that change as motion. It does not perfectly recognize a person. Other moving heat sources can sometimes trigger it, and geometry or environmental conditions can cause misses. The sensor is not shooting a secret beam at you, it is sitting quietly and waiting for the thermal landscape to change. Fact number 35. A thermocouple measures temperature because one of its metals changes resistance, and the electronics convert that resistance directly into degrees. Two metal wires meet at a small junction. The probe goes into something hot or cold, and a temperature appears on the display. That looks a lot like a simple resistance-based temperature sensor, and thermistors and resistance temperature detectors really do use resistance changes. But a thermocouple is deliberately made from two different conductors, and its central operating principle is not simply resistance change. A thermocouple relies on the Seebeck effect. Two dissimilar conductors can produce a small electromotive force related to the temperature difference between the measuring junction and a reference point. The instrument measures that tiny voltage, applies cold junction compensation and calibration relationships, and estimates temperature. The sensor does not contain an absolute degrees signal waiting to be read. It works through a thermoelectric relationship. A thermocouple is not asking, how much did this wire's resistance change? It is listening to a tiny voltage created because two different materials respond to a temperature difference in their own way. And if you think a bathroom scale literally speaks in pounds, wait until the next 5. Reflective clothing, smoke alarms, wetsuits, and metal finishes all trick us because of what their surfaces look like. Fact number 36. A digital scale contains a sensor that directly detects how many pounds of mass are sitting on top of it. Step onto a bathroom scale, and the display jumps to a number, maybe 176, 4 pounds. Because the interface gives you exactly the unit you care about, it feels as though the internal sensor must be measuring pounds directly. But the hardware underneath the platform is not reading a label attached to your body. Many electronic scales use load cells equipped with strain gauges. Your weight applies force to an elastic element, deforming it by a tiny amount. That deformation changes the electrical resistance of the strain gauges, often measured through a Wheatstone bridge circuit. The electronics amplify and calibrate that signal, then convert it into the mass or weight units shown on the display under the expected local gravitational conditions. Temperature, loading position, mounting, and calibration can all affect accuracy. That is why calibration matters. The number on the screen is an interpretation of a physical signal. The display speaks pounds. The metal underneath only knows it has been bent by an extremely small amount. Fact number 37. The reflective strips on a safety vest produce their own light in the dark, like glow-in-the-dark material. Drive toward a road worker at night, and those strips can appear to light up with astonishing intensity. From the driver's seat, they look almost like little lamps sewn into the clothing. Since glow-in-the-dark stickers and paints also exist, it is easy to assume the vest charged up earlier and is now releasing stored light. But turn off the headlights, and the effect disappears. Retroreflective materials are designed to send a significant portion of incoming light back toward the direction it came from. They can use tiny glass beads, microprisms, or related optical structures to do that. That is why they look especially bright to an observer located near the light source, which is exactly where a driver's eyes are relative to the vehicle's headlights. Some safety garments may also include fluorescent or other special materials, but retroreflection itself does not create photons from nothing. The vest is not producing light. For traffic safety, it does something smarter. It sends your own light back toward you. Fact number 38. A smoke detector works like an electronic nose that recognizes the chemical smell of smoke. Something burns in the kitchen, the air smells terrible, and the alarm goes off. The timing makes the explanation feel perfect. Gas detectors can respond to particular chemicals, so it seems natural to picture a smoke alarm smelling combustion. But smoke and smell are not the same thing. The two classic household smoke detection approaches respond primarily to particles through physical mechanisms. A photoelectric detector uses a light source and sensor arranged so that smoke particles scatter light into the detector. An ionization-type detector monitors a small electrical current in an ionized chamber and responds when smoke particles disrupt that current. Neither system needs to recognize the odor of something burning the way a nose does. That is also why carbon monoxide requires a different type of alarm. The detector is not deciding that the room smells smoky. It is detecting particles changing light or electrical behavior, where, moments earlier, there was relatively clean air. Fact number 39. A wetsuit keeps a diver completely dry, and that is why it prevents heat loss. The suit looks like a tight second skin. If its job is to protect you from cold water, keeping the water away from your body seems like the obvious strategy. That is exactly how a rain jacket works on land, so carrying the same logic underwater feels natural. But an ordinary wetsuit is called a wetsuit for a reason. A small amount of water can enter between the suit and the body. Neoprene contains many tiny gas cells that provide insulation, and a properly fitted suit limits how quickly fresh, cold water can circulate through the space next to your skin. The water that enters can warm, while the suit reduces continuous flushing and slows heat transfer. Thickness, fit, water temperature, activity, and other conditions all affect how warm the system feels. A dry suit uses seals and a different design philosophy to keep the wearer much drier. Wetsuit and dry suit are not two marketing names for the same idea. One manages some water while fighting heat loss. The other tries much harder to keep that water out. Fact number 40. Anodized aluminum is just aluminum covered with a layer of paint or plastic. An anodized flashlight, laptop part, bike component, or aluminum trim can be black, red, blue, or another color. Since the color sits at the surface, paint feels like the obvious comparison. A lot of protective finishes really are separate coatings deposited on top of a base material. Anodizing is different. During anodizing, aluminum is treated electrochemically in an electrolyte so that a controlled layer of aluminum oxide grows from the metal surface. During parts of the process, that oxide structure can be porous enough to accept dyes, after which it can be sealed. So the finish is not simply a conventional paint film sitting on top. Part of the surface itself has been converted from aluminum into aluminum oxide. That oxide layer can improve corrosion and wear performance, although it does not make the part indestructible. Paint dresses the metal. Anodizing makes the metal's own surface transform. We have 5 facts left, and everyone hides a transformation. Powder becoming a film, glass fusing to metal, foam that seems to remember, and sensors that read fields without touching anything. Fact number 41. Powder coating protects an object because dry powder is electrostatically stuck to the surface and stays there forever. If you have ever watched powder coating being applied, the fact is almost unavoidable. A cloud of colored particles lands on the metal and clings to it. The process looks like static electricity is doing the entire job. So it is easy to imagine the finished coating as a layer of powder that simply learned how to hold on really well. But a properly finished powder-coated surface is continuous, smooth, and resistant to ordinary handling. If it were still loose powder, every touch would leave pigment on your hand. In many powder coating systems, particles containing resin, pigment, and additives are electrostatically charged and deposited on the part. The coated piece is then heated so the particles melt, flow together, and cure or cross-link according to the coating chemistry. Electrostatics helps get the material onto the surface. The curing stage creates much of the durable final film. The powder is the delivery format. The finished coating is born when millions of particles stop behaving like powder. Fact number 42. The glossy enamel on a metal pot is basically plastic paint that dries on top of the steel or cast iron. It has color, shine, and a surface that can chip and reveal a different material underneath. Visually, that is exactly what paint does. The word enamel makes things even more confusing because it is also used for certain conventional paints. But vitreous or porcelain enamel is made through a very different process. Mineral materials are prepared as a glass-forming frit, applied to the metal, and fired at high temperatures so they form a glassy layer strongly bonded to the substrate. The result can be decorative, stain-resistant, and durable, but the coating itself is inorganic and glass-like rather than an ordinary plastic paint film. That also helps explain why a sharp impact can chip the enamel and expose the metal beneath. It looks like paint because it has color. Its manufacturing story is much closer to fusing a skin of glass onto metal. Fact number 43. Memory foam permanently stores the shape of your body and remembers exactly where you slept every night. Press your hand into a memory foam pillow or mattress, and the imprint hangs around for a few seconds before slowly disappearing. The name makes the interpretation almost irresistible. It seems like the foam recorded your shape. There are also real shape memory materials that can return to programmed forms under particular conditions, which makes the word memory sound even more technical. But ordinary commercial memory foam is typically a viscoelastic polyurethane foam. Its behavior combines elastic recovery with time-dependent deformation and energy dissipation. Pressure and temperature can influence how quickly it deforms and returns toward its original shape. If the impression disappears, the foam has not stored a permanent map of the person who made it. Long-term wear can create lasting indentations, but that is material aging or damage, not the mattress remembering its owner. Memory foam seems to remember because it takes a little while to forget the pressure, not because it learned who sleeps there. Fact number 44. A HEPA filter removes gases, odors, and volatile organic compounds because HEPA is basically the highest level of household air purification. You see the term on vacuums, air cleaners, clean rooms, and medical equipment. Culturally, HEPA has become shorthand for serious filtration. That makes the next assumption feel reasonable. If it catches extremely small particles, then even smaller odor molecules and gas molecules should be easier to trap. That is where the sieve analogy breaks. A gas molecule is not simply a tiny dust particle trying to squeeze through a hole. HEPA media are designed primarily for particulate filtration. Within the fibrous filter, mechanisms such as diffusion, interception, and impaction help capture airborne particles and aerosols. Gases and many volatile organic compounds require different removal mechanisms. Adsorbent media such as activated carbon or other specialized materials may be used for certain gases and odors. An air purifier can combine HEPA with carbon, but the carbon does not magically appear because the first filter says HEPA. HEPA can be excellent at its job. The fact began when we decided that doing one job extremely well meant doing every job. Fact number 45. An electronic magnetic sensor works because the magnet physically pulls on a hidden metal switch and closes a contact. Bring a magnet near a lid, motor, wheel, or electronic device, and something changes state. The easiest picture is a tiny mechanical switch inside getting tugged by magnetic attraction, and that mechanism really exists. Reed switches use ferromagnetic contacts that can move when exposed to a magnetic field. The mistake is assuming every magnetic sensor works that way. Many modern magnetic sensors have no moving contacts at all. Hall effect sensors use a semiconductor element in which a magnetic field can produce a transverse electrical signal when current is flowing. Electronics then condition that signal to create an analog or digital output. That allows a device to sense the presence, strength, or in some designs, direction of a magnetic field without any hidden lever clicking into place. A reed switch and a Hall sensor can perform similar jobs while relying on very different physics. The magnet does not always have to pull a piece of metal. Sometimes it only has to change how electrical charge moves through a semiconductor. After 45 facts, the pattern is hard to miss. Our intuition usually does not begin with something ridiculous. It begins with a useful analogy, and then stretches that analogy too far. A filter becomes a universal purifier. A surface finish becomes the entire material. A familiar name starts pretending it is a scientific definition. Curiosity gets better when we ask a few harder questions. What is the sensor actually measuring? Where is the energy coming from? What material is really changing? And which part of the explanation existed only because it sounded convenient? The everyday world did not need extra mystery. It already had more than enough hidden mechanisms.